So you won't need it division.
No.
Can you switch it off?
So I just close it.
Close the lead.
But this will still come out.
Yeah, that's okay.
Oh, that's what I said.
Switch on. No, turn the उसका ये होगा.
So,
If I'm correct. I'll do this now. Second.
okay.
Okay, so good morning everyone. So this kind of summarizing some of the stuff we discussed yesterday. So this is for overdamped transfer equation. So this is simple particle because equation has a deterministic part and a stochastic part. So the deterministic part consists of a gradient of some potential, and this potential could in general depend on some external parameter lambda of t, which I can vary with time. Okay, so that's like the example that Edgar gave about trap potential or the center of the trap being controlled as a function of time. And then this is a non-conservative force which can be written as gradient of a force. And then the noise is Gaussian, mean 0, and correlations in time are it's uncorrelated in time, and the strength is 2D, where D is the diffusion constant with KBT diagram. So why is this the diffusion constant? If you switch off the force, then you can show that x square equals to x square average goes as 2dt. So that's why you can identify this with the diffusion constant. Okay, but here in general, if you have a force, of course, it's not diffusion. I mean, it will. If it's in a trap, it can't diffuse forever, right? So it will saturate after some time. But it's always, you see, it has a stochastic motion. And then what we said is, the first law of stochastic thermodynamics is some statement like this, where so in a given trajectory from time 0 to time t, we observe the trajectory of a particle. For a given trajectory, one can compute all these things like what is the change in energy. So change in energy is just, okay, I didn't write that. So delta U is just E of x at time t, minus x at time 0, 0. Okay, so this is just the change in energy. So this just involves this potential at time 0 and at time t. So the particle has evolved, so you have to take the position at time 0 and then the time differential. So energy is just a differential, so it just depends on the endpoints. But you can also compute, so you can ask what is the work done on this particle in this trajectory. That is something which depends on the details of the path. Okay, it's a function of that entire path. So the entire path I am denoting by this curly bracket x of tau. So tau goes from 0 to t. Okay, so it depends on the entire path, and it's this functional. So you have to integrate it over this quantity. So right. So this is the from the time dependent part, and this from the non-conservative force. So in general, you can have either of them non-zero, and you would still have work done. And heat is given by F. So F is the total force into x dot. And then yesterday what we discussed is that things like this have to be interpreted in this Stratonovich sense, right? So it's so one should put some dot here maybe. Okay, so okay, and then we started discussing the sort of equivalent of the second law. And for that, what we needed is the probability of forward trajectories, because second law is about like I mean things happen with more probability in some direction, right? That's what the second law tells us, that I mean there's a natural direction of time, and so this forward direction is more probable than reverse process, right? I mean like a typical example.
In a priori sense, because if I dot x dot is capital F, but in capital F contains the small f.
Yeah.
Okay. And the small f dot x dot again appears in the W.
Right.
So it's like, so far as dictating is concerned, the two things have been split fine.
Right.
But if I want to get an a priori meaning for the W, that makes sense, because there is a potential, there is an x. Now this delta Q, how do I think that I can independently get it? Because it seems to be defined in terms of again those two quantities. So then what's the independence of this delta?
Right. Okay. Okay. So, but yeah. So that it is a tricky question. So this, of course, you agree, right? This, I mean, I can split it up.
Yeah.
Basically, the energy I have split it up into two parts.
The mathematical steps of the splitting is fine.
Right. Yeah.
But
now you are
still interpretation.
Okay. So this, I mean, in the underdamped case, it's more maybe clear. Okay. So let me just write that case. That maybe that's. So the case it's f of x, and then this is the force from the path, right? Minus okay, so then and this is equal to minus del p by del x. and then what I do is the usual thing is just to multiply this by velocity, so that that would give me ddt of so multiply by velocity, so that gives me mv square equals to minus
Let's say two sources were independent from this. One is the bar part.
right, yeah. So this is coming from the bar, and this is coming from the potential and the.
But here,
Right, yeah. So here, I mean, okay. So here, here you have no problem, right? Here is everything is very clear.
yeah.
Right, yeah. So let me just complete anyway. So here you can show that ddt of u, where u is half. So this one just requires some rearrangement of writing date using the fact that dv is equal to dv. Okay, so I use this in here and I get this. Okay, so now here it's clear that this is equal to, so this is the rate at which work is done, dw by dt. And this is heat from the bar. Okay. Now here actually what I mean, if you think about this f x dot, it's actually that only. It's exactly this quantity. Because see if so if you look at the equation of motion was in the overtime limit, it was gamma x dot equals to f plus eta. Right? I can do the same thing. So you can see that minus f is really equal to minus gamma x dot plus eta. So when I write f minus f x dot, it's actually exactly this object. Okay, so in this overdamped limit, I mean, it's clear that, I mean, but you are not overcounting or anything. It's just, I mean,
in the undertime,
yeah.
the equals defined in only one way. You did not have to then go back to the equation to define it.
Right, yeah.
So here
Yeah, but here because I have neglected velocity, I mean, like, so, I mean, so therefore, this is, but, yeah, but in some sense it's okay. It's all very, see, this also connects with, it's exactly the definition you are using in the underdamped case. Okay, and here the only difference is that this is gone now. Right, otherwise, I mean, so that's another way to sort of justify it. Yeah.
I want to ask the same question in a slightly different way.
Yeah.
The content is the same. See, when Edgar was changing work and so on and so forth, he was changing the potential
Yeah.
and then also the temperature, and thereby he was using equations like this to, I don't know whether it is measure or calculate these quantities. But can you calculate delta Q and delta U independent, and then independently, because else how will we get the validity?
Right, yeah.
So
Yeah,
that
so
is my
that,
question in connecting the two, and maybe it's, yeah.
Yeah, okay. So experiment, I don't know, but in a simulation, it's very easy, right, to compute this and this separately. I mean,
And del
here
Q?
this
Del
also,
Q?
huh? Yeah, yeah. This also, I mean, in a simulation, I mean, you know exactly what this object is. I mean, it looks like this is almost the same. That's what Deependra's problem is. But they can compute them. There is no problem, and they satisfy this law and so on. Okay, now I mean, okay, I don't know if it's okay. I don't know what else to say.
Just 1 second. So if, okay, sorry. Go on.
Yeah, but I mean, I'm saying numerically in a simulation, it's you can independently compute this. You can independently compute this.
Only the second one from the equation of this.
From the equation of motion, right? And using that Stochastic definition, right?
But I mean, here small f dot x dot.
Yeah.
This is also included in the second part and the first part.
Yeah, that's what his problem is. But I mean, okay, if you don't like f, you can replace it by x dot minus v. You can write it in this form.
I mean, that's we can do.
But yeah, it's in some sense. I don't know. Anyone else wants to comment it? Go ahead.
No, for your question about experiment, in the end, experiment is a very expensive simulation because
It's a
it's a very expensive simulation
Yeah.
because you will get data, stochastic data from the experiment.
Oh, okay,
You are
okay.
plugging in the experiment. You of course need to know the potential from the experiment, the forces, friction, etc. But it's not that different from simulation.
Right.
In some experiments, they can measure the heat independently.
mostly you are following the stochastic path and the force, and it's like a okay.
Yeah.
It's an expensive numerical simulation.
But when you also talk about simulation,
Yeah.
you mentioned the full system, right? So a particle and a path.
Simulation means you have to simulate, no, not path you forget. You just simulate this equation.
Noise you take it as an effective path.
Yeah, at each time you just choose a random number from some distribution.
So capital Fx is defined by that equation,
Yeah,
left
it is.
side equation.
Which one?
The right side is just an equal.
This one. Yeah, if f is defined is like this.
See, that is where my problem is.
But you're saying because
I'm
I
saying
can
it's
put.
not defined by that. Left side equation.
No, here I
defines-
mean this is the equation of motion where f is given by this. That is.
F is related to.
Right. F is equal to this. I mean that's how the definition of the force.
But its meaning has come from that equation, separate.
No, no. See, when I looked at the derivation of this equation, it started from this equation and then I dropped this and because here everything was f of x was just this, right? So I just dropped this term and I took this there and I got that equation, this equation.
Yes.
So it starts from the, I mean basically this is completely, everything is well defined, right? It's not defined in terms of something.
So
Moreover,
what I'm trying to say is that when you calculate delta Q,
Yeah.
then operationally you are again going back to the equation of motion there, that left side. Px is equal to what?
Yeah, you can write it, but you can also use this definition.
But then there is a confusion, right? If I said V is equal to 0, for example,
Okay.
then there is no difference between W.
If V is equal to, then of course delta Q and W are the same because there is no change in internal energy. So then it is true that this is 0, right? Because there is no change in internal energy when you.
I mean, this cancels. I mean, W minus delta U cancels the portion which is coming from F dot x dot, right? Because by definition, delta U is equal to W
Right,
minus
yeah, yeah. Yeah, but I think let's not spend too much time and with other enough. Okay, then let's go to the second law. And so what we said is, again for this system, let's quickly recollect what we did. Is I wrote the property of forward trajectory. Of this trajectory going from x0 to x, so this end point I call it xn or xt. So and that is given by and I divided it by the probability of the reverse trajectory. Okay, so how is the reverse? So forward, there is forward path from x0 to xn, or let's say xt, and this is some x of tau but the forward trajectory also involves the specifying the time-dependent protocol, which is lambda of tau. So this completely specifies the forward trajectory. So the reverse trajectory is, okay, you come back like that, but so x reverse of tau is equal to x of t minus tau. So at time, if you say tau equal to 0, it's to this point. If at tau equal to t, it's back here. Right? So that's the protocol for the reverse path. And for the force also you reverse it. Okay? So you write this as lambda t minus tau. So it sees the same force while coming back as it saw here. Okay? So it's this, yeah.
So I just had a confusion. So when yesterday Luca was doing something similar,
Yeah.
he had the dual time distributions. Is that because his was a jump process,
Right, yeah,
whereas
yeah.
yours is a continuous trajectory?
Right, yeah. So yeah, I'll come to that also briefly. But yeah, here, so there you wait for some time jump and so on. So you will have to put that in. Okay. Right, so this is the reverse path, and so you will just put the probability of that path out here. So you can start from this end maybe. So what is the probability? So this is the first step, right? So it goes to xn minus 1, even it was at xn. And then you keep going back. The last time you come back to x0, given you're at x1. And then you put some here, p of n, xn. Okay, so now what are these p0 and pn? So these are some probability distributions that I choose x0 and xn from. Okay. So the probability of the entire path is what is the probability of choosing x0 from some given distribution. So this I can, this is, I haven't specified this yet. Okay. So this is something I can choose. I have some freedom to choose this distribution. So given x0, I choose x0 from this distribution, then what is the probability I am at x1 given x0, x2 given x1 and so on. This is, I can write this for because it's a Markov process. Okay, so now what I use is, we said that we could compute these transition probabilities and we found the ratio, and what we got is okay, so this one I'll keep separately. So this I can write as yeah.
Will not be there Pn xn in the terms in the denominators, the initial condition, the initial probability distribution.
Yeah, this one.
Or this one could be, I mean,
Yeah, I can write it at this end, but I mean, I'm just doing it here. Yeah, I started from here, yeah, that's true. And then I move like this. In time, I move like this, but yeah, that's true. But I just put it here.
here, but that.
Right, yeah. Okay, so now I'm just taking this upstairs and then writing this as P0, X0. And what we showed yesterday is that this ratio, this particular ratio is minus plus plus. Okay, where delta Q is this object. So, right. And then this, so this we identify as change in and this is change in Okay, so why is this changing? Because I can, so what I had said is yesterday is that given a probability distribution associated with the initial system, so let's say whatever P of x, then I can assign entropy to this distribution. And then, of course, here what I need is entropy of a single configuration, right? X for a given configuration. So then I just interpret this as that this is the probability of a configuration, and then this is the entropy of that configuration. Okay, so this allows me to define the entropy of a given configuration as this object. So therefore, this is the entropy in the when it's in configuration XL, and this minus this. So this is the change in entropy of the system, right, when it goes along this path. Okay.
So when the system is in some position x, you are associating that entropy S of x, some configuration x.
Right. Yeah. If it's in
But
a
P
state
of x is an underlying distribution that is ensemble averaged over all configurations.
P of x is some probability distribution. It could be, for example, the equilibrium distribution. So this is the distribution it starts from.
But that is not a single trajectory quantity.
No, it's not. It's just associated with the initial condition of the system. It's not related to the trajectory. Yeah. Okay. So. Okay. So this is what is the this is the definition of so this entire quantity in bracket is what I define as delta S total multiplying. Okay, and
trajectory entropy only, right?
yeah, so this is the entropy generated on this trajectory, which has part of it depends on this detailed path, and is basically the entropy gained by the environment, and then I'm associating some entropy which comes from this this change in the state
For the system.
for the system.
That's also like for a path, like it is just the path definition that you are using.
But this, you can see it depends only on x naught and the initial and final. Right. Final, of course, depends on, because the path also contains these 2 points, but it doesn't depend on the details of the in the path.
But it's not like the average entropy of the system at
No, right, yeah.
It's still a path quantity.
Right, yeah. Right, yeah. Okay, so other interesting point that you should note is that this quantity is sort of extensive in the sense it grows with time. If you look for a long time, it will grow. While this kind of quantity is kind of bounded, because if at least for a particle in a trap, you can imagine that this doesn't grow indefinitely, but this can actually scale with time. Okay, and right, yeah. So there are some things called steady state fluctuation theorem. So you might have heard of Gallagher-Cohen and so on, which state relations for this kind of quantities. Okay, where which is true only in the large time limit. Okay, but what I'll talk about is valid for even short times. These are called transient fluctuation theorems, where you actually need to include this term. Okay, so then let's go to the once we have yeah.
Could you tell me how, again, we compartmentalize, this is the large contribution of the
I mean, see, right now you can just take this as definition. I mean, because this was very clear, right? It's the some heat goes to the air and then. Okay, now this part is a bit strange. I mean, but it's like that. So right now, I mean, you can take it as a definition. You put this. I mean, so I gave you some motivation, like I mean, so. Like for the system, we just want to define an entropy for each configuration. Okay, so usually entropy is defined for an ensemble, right? for example, when you calculate microcanonical entropy, it's for the microcanonical ensemble. But here, so that's why I started with this definition. Let's say the initial point is chosen from some distribution, okay, which is let's say P naught x. Okay, then I know that it has this is the entropy associated with that distribution. Now I interpret this as probability of finding it in this configuration, and what is the probability that what is the entropy in that configuration. Okay, so that's just how the entropy of a given configuration will be.
Same distribution.
Okay, first I'll take.
The P0 and Pn have to be the same distribution.
No, this is no, it need not be. This is completely in my hand. So I'll come with the various choices.
So you're picking them out of the initial, you're picking the initial point out of the distribution.
Right, yeah.
So x0 and xn are inputs initial points.
Yeah, but they are two different endpoints, right? Here there's one endpoint and endpoint. So right now in this derivation, I'm free to choose these two distributions.
Different.
Yeah.
So the path dependence comes into that middle term, so that
Path dependence.
because you are looking at one particular trajectory.
Right, yeah. So this term will
This term will
contains.
depend on which trajectory.
Right, yeah. But this one is kind of independent of trajectory. That's true. And like I said, at large times, this is the dominant term. This scales with time. Okay. You can imagine, right? The heat absorbed will grow with time.
So in the overdam, I mean, we are considering like velocity contribution is not there, right?
Velocity is not there. Right, yeah.
One additional question. So there is a P0, H0 and Pn xn.
Okay, yeah.
Is that 0 and n subscript also required for?
Kind of, yeah. So yeah, it will become clear when I write. Okay, so what was the first? Okay, yeah. So the first thing I wanted to say, which I already said yesterday, was that so now this omega, the way I defined it, it's a function of basically it's a function of the entire trajectory, right? So I can write it as x of tau. So this is the entropy generated in this part. Okay, so now what I can do is I can just bring it this side, e⁻ minus omega is some function of all this x naught to x n. And then I can integrate over all x naught to xn. Okay, so then since I'm summing over all trajectories, this is equal to 1. So I therefore get e to the power minus w average over all trajectories where the initial point has some distribution. So this is over all forward trajectories. Okay, starting from some initial distribution P naught. I don't care about the final distribution Pn because this one has only information on P naught, right? So I choose x naught from that distribution and sum of all possible trajectories, and I average this quantity. So this is equal to 1. So I think probably this was. so this is one fluctuation relation, and one thing you can immediately conclude from here is that so there's this inequality that I think for any convex function f of w, you can prove that this expectation is greater than the expectation of this. So if you take the expression inside, this is always greater than. So this implies that so this, since W is the entropy produced in a path, you can think of this like it's kind of like second law. So it's not right to really call this a second law because second law has different meaning, but it has similar form, like entropy produced in any natural process is always greater than equal to 0. Okay, so now let's see what else we can. Yeah.
Should we put a class subscript for all these averages? Because these are
Forward, right, yeah. So, yeah, we could put, but everything, yeah, typically will be interested in forward path. The reverse paths are usually just to help in the calculation, but most quantities that we'll calculate will be for the forward path unless explicitly mentioned. Okay, so the next thing that we'll be interested in is what can we say about the distribution of this quantity omega.
Abhishek, can I ask one? So you derive this equality, right, and then you use the theorem to
Right,
the inequality on the delta. But does the equality contain any more physical information?
Equality would be true for probably like quasi-static processes.
No, I mean on the average e to the power of minus w equal to 1.
Right, yeah. Oh, this
This
is of course always equal, right? Yeah. Oh, you are asking whether this has any additional
physical information.
Okay, so what you can do is that you can use it to derive, for example, things like linear response. I mean, like yeah, you can use. Not this one, but other fluctuation theorems, you can use them to derive linear, like linear response theory. This one also probably, I'm not sure actually, right here. It's just a nice equality, I would say, at this point. Okay, so let's see what else we can get out of this equation.
So, what is the basic difference, means why you are not saying this one is the actual second law?
Okay, because see, second law is a statement about, I mean, about macroscopic systems where you don't care about ensembles and all. It's what you see typically in a like single realization of the system. But here you start with a Langevin description and it's all sort of, I mean, there's already a lot of post-training going on.
You need an average in here, that's why.
Yeah, but also the first point would be that the second law is a statement really about, I mean, okay, strictly speaking, it's about macroscopic systems. Okay, and it's more related to what, like typical behavior that you observe in because of large numbers.
Isn't that the same here? Because you already have a constraint. The Langevin equation means you have huge number of degrees of freedom hiding behind somewhere. And then you are doing averaging of
Right, yeah. But I'm saying because you have done so many things, you can't call it a, okay. Okay, this one actually I'll discuss in the next, that is the topic of my kind of presentation.
No, what is the meaning, physical meaning like, I mean,
of
this statement, what we can say like. So, can I say like if in any mesoscopic system the probable change, whatever spontaneous change will be there, that will increase the entropy of this of that mesoscopic system or any.
No, see, I mean, usual second law has some meaning. But this one, okay, no, I didn't understand your question. You are asking what is the physical meaning of this equation?
Yeah, I mean, what I am saying, so for example, here my system was in the x naught, it went to xt,
Yeah.
or I was comparing two forward and backward trajectory.
Right, yeah.
So, like, that leads to this result. So, it means that entropy change, whatever will be happening in the system.
Is so basically okay. Yeah, one thing it contains is that in a forward process, is more likely. Then okay, actually the next. Let me prove the next statement. It will become clear that this statement at least give you what is the probability of a forward process happening compared to the reverse process. Okay, so reverse processes are much unlikely, and how unlikely is it depends on how much entropy is produced. Okay, it's exponential of the entropy produced. Okay, that's one. Physical meaning of the equation. So from here, maybe that's not so clear, but let me write another theorem.
So this means that the entropy, if I consider over a single trajectory, it could be positive, negative, whatever. Now when I'm averaging over a large number of trajectories, it has to be greater than equal to 0.
Right, yeah. So, this is, this is the distribution of probability produced in a given time t. So there's always some chance of A, but the fact that this quantity is equal to 1 tells you that these things can't be too, you can't have too much weight out here. So, so the next statement that I'll write makes it more clear. The next theorem that I have to. Okay, so supposing we want to compute this object P of P plus of omega, right? Probability that omega entropy is produced in the forward trajectory. So how do we do this? So this is basically given by we just do integrate over all these paths. And then we had whatever distribution. Let me just write the one sec. The entire path is of tau.
So I have a nice question. So this notion of this backward path,
Yeah.
is it like more for mathematical convenience, like a construct, because it helps us to get this derivation? Because experimentally, so like in Lucas-Stoch, like when you see jumps, so the backward path has these jumps or transitions exactly at the same points.
Right, yeah.
Intermediate.
Yeah, it's just a tool to, see, those are extremely unlikely. Right? That's what this theorem is trying to say, that forward trajectories are more likely than the reverse trajectories. And how unlikely that is depends on the entropy produced in the path. Right? It's the forward trajectory is exponentially more likely. More entropy is produced, they're more likely. That's the main. And like I said, this entropy omega, it scales with time, right? So if you look for longer, then it becomes even, those trajectories become even more unlikely, reverse trajectories.
We had this result yesterday also, where you know C plus by D minus equals exponential of S bar.
Did I write that?
Yeah.
Which one? No, that is that one, right? It's up for the path, but now I'm writing for the distribution of omega. That was the probability of the paths, forward path by reverse path. But now I'm asking what is the entropy produced in the forward path by the entropy produced in the reverse path.
I'm asking the question that you have written over there.
Right, yeah.
It was similar to what you wrote yesterday also.
Yeah, this I wrote yesterday. But now what I'm going to do is a bit different. So now I'm going to look at the distribution of omega, the path. Okay, so this is P of plus. And then we said that, so this is the probability of the forward path, and this is equal to from that theorem, so let's call it P of plus, the probability of the forward trajectory. Now from there, this is equal to e to the power omega for the forward trajectory times P of minus the reverse trajectory. Okay, so now if we, what we can also see that the entropy produced in the forward trajectory is equal to minus of omega produced in the reverse trajectory. That is easy to check, and obviously, so entropy had two contributions. Okay, so you can see that one is from the heat absorbed. So if you go reversely, of course, heat will go into the system, right? From the if heat went to the bath in the forward trajectory, in the reverse trajectory, it will go into the system, and the system part also just gets reversed. Right? So the entropy in the forward and reverse are just minus of each other. So using this, I can change. So first of all, because there's a delta function omega minus omega plus, I can take this outside. Right, so I can take this omega, I can just bring it here to the power omega, and now I can replace this by omega plus is minus of omega minus, so I can call it plus omega minus. Okay. So now what is this object? This is in the reverse trajectory. What is the probability of producing minus omega entropy? Okay, so this is equal to e to the power omega. Okay, so this is our next fluctuation theorem. P forward probability of producing entropy omega divided by P minus probability of producing minus omega is equal to e to the power.
There is a time dependence hidden in the omega itself.
No, see, this is just a dummy variable. I'm asking what is this distribution function. So there is no time in this, I don't know. It's just the distribution of this quantity. But so I look at all possible paths starting from my initial here to here and just look at the distribution of this quantity. Yeah. It's the same, right? Because it's just the reverse.
It's the same quantity.
It's the same.
So the only difference between that top formula is it was talking about path, here you have just converted into entropy.
Entropy, right, yeah. So now it's, yeah, there it was just probability of trajectories, right? That is more detailed information. This is just about the entropy produced in those trajectories.
So if I extend this for the undertime case, now it should be xv with the minus x minus.
Exactly, right, yeah. So this I won't have time to work out, but it's exactly the same steps, and only thing is forward trajectory is x tau, theta, lambda tau, and so this is forward, and the reverse trajectory is x. So you have to reverse velocity, but otherwise it's the same.
And for the entropy contribution, now you have a delta Q coming from the transitions, and the entropy of the system.
Entropy will,
xv.
right, yeah. So entropy, I mean, the heat contribution will again be just this. So this will be the change in minus.
So the difference is coming because there are many p pluses for the forward trajectory, then there are p minuses for the reverse trajectory. That's what we are integrating. So can I think in that way? So say your is happening, right? Like there are millions of forward trajectories, but just like hundreds of reverse trajectories.
No. Yeah, first of all, you can't count, of course.
No.
But I mean, it's less probable, but it's not like there are more.
In the sense, like if you do an experiment, right?
Yeah.
Like, then you can say you can count them as well.
I always can construct a reverse trajectory.
Yeah, this is by hand we are constructing the reverse trajectory.
Yeah.
In an experiment, we may not
Experiment,
see. Yeah, in an experiment, of course,
Say you
if
do
you
experiment for 1 minute, right? Say
Right,
you
yeah.
have a way to count that. So in 1 minute you will say million times it's going forward, but just 100 times it's going. I'm just making these numbers.
Okay. Yeah, if you reverse the protocol, okay.
So within that limited time, I'll see less, which translates to probability eventually.
Yeah, you will see those, it will be much less, I mean, of course that is true. You will see those trajectories happening much less time. I mean, if you just do nothing, just let, okay, so first of all from x0 to xt, if you even forward, of course it's hard to get trajectories exactly ending at some position, right? But let's say you count.
Lost coins or something, right, where you can count it.
Yeah, but I'm saying even if you toss points, making sure that your end point is exactly the same, that is hard, even in a forward trajectory. But it's true that the reverse things will happen much less. Okay, right, okay, so this now let's try to extract some more information from this relation. And actually you can prove things like Jarzynski's equality from this theorem. Okay. So now what is important is to choose those P0 and Pn that I have defined. I have some freedom, right? I haven't specified those yet. So using those, I can come up with special cases and including proof of Jarzynski's relation. What is this? Okay, so what was W was delta S total by is equal to
I mean, in all this calculation, what assumption is breaking this symmetry of forward and backward?
I mean, there of course both are. Both are valid processes. It's just the paths are more or less likely. Yeah. Right, yeah, so that's why this reverse path was with minus. It's for the backward process. Huh? Right, yeah. But backward and forward are the same variables, right? No, this is because it's for the reverse trial. Because the initial P of n is a different distribution, right? So under certain conditions, I can make it equal. So I'll discuss that.
Do you integrate over x0 and xn as well when you calculate?
Yeah, I mean, it's integrated over everything, right? So that's what I wrote, x0 to dxn.
Sir, are these theorems valid for all kind of nonequilibrium states? I mean, we are not assuming anything regarding these forces or anything if we are getting to some steady states.
No, of course I derived it for this particular set of equations. It's also true, I said, for underdamped equations. It's also true for jump processes. But it may not be true for some non-equilibrium, not every non-equilibrium process. Anything which you can write in this form is okay. Like right now I'm sticking to Markov processes with certain properties of the path, like detailed balance and so on, which is incorporated in this noise terms. So like in Lecture-2, we saw that detailed balance was very important, right, to establish this. So that in the dynamics, detailed balance has to be there, which comes from the fact that we have a thermal bath. Okay, so
and there is an assumption that the final state will be equilibrium, right? It left for a long time. If you stop the protocol, it will go back to equilibrium.
if I stop the protocol, it will, if I switch on lambda.
Extremely nice times, it is equilibrium.
No, so if, with this process, of course, it's never in equilibrium because of this guys. That will keep evolving for, I mean, it's a non-equilibrium. If there's a time-dependent force, it will never reach equilibrium. Right? It will reach some maybe flow state or something, like a time-dependent steady state. If you don't have the time-dependent part, then it might reach a non-equilibrium steady state, but it won't be an equilibrium state. If I switch off, what is the, so detail balance ensures that if I don't let lambda change with time, if it's fixed at some value, if there's no f, then it will go to e to the power minus beta b. Right? This is the equilibrium distribution. In that case, I can really check for detail balance. But now you can imagine that I have, I mean, so even when lambda t is, it's like local detail balance in some sense. It's changing with time, but at each time the path is kind of trying to equilibrate it to the whatever parameters at that instant. So that's.
You need to write an f dash on that top equation.
F?
See, fx equal to my, no, not there. Yeah, fx equal to, and just add a dash because.
Very small.
That is small.
That is small.
Oh.
Small.
Oh, sorry, this is small.
This is small.
Yeah. This is the non-conservative force.
Yes, that I understood. But I thought both are capital.
No, then it will be even worse.
So right now, whatever we are talking about is just one part.
This is one particle. Yeah, but it's very easy to put an index I and make it n particles. And you can have f which depends on all the x's.
So then
Everything is added.
P is minus change, right?
Huh?
Let's take the P minus of minus W.
Yeah.
That will become even more unlikely.
Right, yeah. I mean, so this already says, right, forward, I mean, but if, here is positive and negative for the reverse process. But let me, in some cases, both can become forward, okay. If so this is what I will now discuss.
So it's mesoscopic in the sense we are talking about one particle. Is it?
So yeah, in one particle, but yeah, but the formalism is valid for like, I mean, 10 particles or a million particles, it still goes through, but maybe
the value of omega probability
will become even more unlikely, right? Yeah. And to get the equality out there will become really hard. When I say W greater than equal to 0, it will typically be probably more. Okay, so now what I was saying is, what is this entropy? So let's just make sure this is correct.
There is a sign difference compared to working velocity.
Huh?
There was a minus sign before.
This one?
What you wrote before?
Oh, sorry, yeah, that's right. And this one is correct, right? Plus.
That also.
Okay, so let's forget KB because it will create unnecessary. So KB will set it to 1. Okay, so this is the, now supposing I choose P of
So, one question. X is a function of time, right?
What is a function of time?
No, X is in this trajectory. When you choose any particular trajectory, X is a function of time.
Right, yeah.
So, like forward trajectory means you this curve is what you have shown. But reverse trajectory means
It's just the same thing followed back.
but in time, like if I have to take this curve and put it like this for
Right, yeah.
time will always be forward.
Right, yeah. Yeah. Okay, yeah. So if you want, yeah, you can flip it and then go like that.
That's
right. Okay, so now, so what is delta S? So it's beta delta Q, and then so if I take minus beta log Pn, so from here I get plus log of S. Yeah, okay. Okay.
So you need some equilibrium distribution for the...
Right, yeah, so I just choose this to be the equilibrium distributions at the two endpoints. Okay, so now if you see that this is delta Q and this is what? V xn lambda n minus V x naught lambda naught was as delta U. Right, so delta Q plus delta U is from our definition, I think we defined delta Q is equal to W minus delta Q. So delta U plus delta Q is just W. So this plus this is W, and then the rest is minus beta delta change in free energy. Okay, so delta F is F lambda n minus F lambda naught. Okay. So this is if the system was in equilibrium at those two parameter values, then what is the free energy, which is just you have to find from this part whatever. So F is minus kBT log Z. Okay, so in this case we see that the change in entropy can be written as beta times the work done minus change in free energy. So now
so the final state can be any, like the initial state has to be of the forward path has to be in equilibrium, and the initial state of the backward path has to be in equilibrium.
Right,
but
yeah.
Final states of both,
right, yeah.
They can be anything.
Right, yeah. So I mean you should remember that, see here I am choosing this, but in the actual when you do the process, you start, let's say you can start x naught from this distribution and you let's say drive it for some time t. At the end of this time the system will be, it won't be in equilibrium, right? It will be in some time dependent state. So it has not reached, it won't reach this state. So even so I'm driving it, I mean unless I drive it very like quasi-statically, then it will be in this state at the end of the process. But in general when I drive it, even if I start from this state, at time t it's not in, it still has not relaxed to an equilibrium state. Okay? If at that time I just wait forever at that temperature, then it will go to this state. I hope this is clear. Any questions?
Can you repeat?
Huh?
I missed that.
No, I'm saying if you see my system, it satisfies some Popper-Planck equation, right? This is what we wrote yesterday. So now I'm saying if you start from p at x t equal to 0, if you choose this, then if you evolve this Popper-Planck, then of course you'll find some p of x t at all times, right? Now at the end time, so if I find this, at the end of this trajectory, if I find what is this distribution, that it's not necessarily equal to this. That's just, I just wanted to mention that. But if you do the experiment, then wait for a long time, then it will relax to this equilibrium, of course.
How do we know that after making the front, after changing the temperature, the final state will be the same?
We know the temperature of the bath. Bath is always at the same temperature, that's the assumption. Unless you do something like what Edgar was talking, put lasers and you can change the temperature by some If you want to make an engine, of course, you can change the temperature. But here and here, it's all constant temperature.
So this would be true for the reverse path also, right? When you are taking.
Yeah.
There also it doesn't come to equilibrium.
It doesn't come to this equilibrium at the end. So this is just, I just put it by hand. I can put anything out here. It is not anything. I mean, so but it doesn't mean that the system is actually in this state. Okay, so this is a change in entropy, and so now if we look at this, so this.
One more question.
Yeah.
So you have one profile for x versus time, right?
Yeah.
And correspondingly, you can also have a profile for lambda versus t.
Right. Yeah.
So when reverse.
Yeah.
So lambda is also reverse accordingly, like.
Yeah, you just follow the reverse, and whatever lambda was, it becomes lambda at sine 0 for the reverse. I wrote right lambda of.
Okay, I mean t minus tau. You have it.
Okay, so now what I wanted to say is that this is related to W, this quantity, and so you can ask now what is the so see, delta F only depends on the endpoints, right? It in fact depends only on lambda at the ends, not even the trajectories, because free energy is just depends on the parameters lambda. So this has no information on the path or the position, the configuration at endpoints or anything. So this is just a function of still the trajectory. Okay. So now I can ask what is the distribution of W instead of asking for the distribution of omega. So and because it's just linearly related, so I can rewrite this as P plus of W by P minus of minus W. So where W is the work done in the forward trajectory. Okay, so this is always forward trajectory whenever I write this. This is the change in free energy in the forward trajectory. Now from this I can do the same trick. I just take it this side. So I do P plus W. And then I integrate over d of all possible W. Okay, so this gives me basically e to the power minus beta W average is equal to okay, so so this is what is known as Jarzynski's gravity. So the idea is in some non-equilibrium process you just and so for example in the simple experiment is you take a polymer and pull it and ask how much work is done. Okay, and then you do this experiment many times and take this average. You find that the change is exactly equal to the change in exponential of the change in the free energy from one configuration to another configuration. Okay. So it simply follows from this statement, which was I think this was is proved by I think first by Crookes. And this Jarzynski is 1997. So so first this Jarzynski equality was actually proof for a Hamiltonian system where it's much simpler proof, but you can for stochastic systems, and this is one sort of easy way to prove this theorem. Okay, so now I'll state one last result that you can extract from this by just making a different choice of this P0 and theorem. Any questions? Yeah.
This W plus and W minus are usually different.
W plus and W minus. Yeah. W plus I said is equal to minus this omega, right?
Yeah.
Omega plus is just minus omega minus.
Same process can be, similar process can be done for omega like minus as well. By just putting omega plus is minus omega minus. Omega minus is
Yeah.
minus omega plus.
Right, yeah.
Why are we like keep on saying that forward trajectory, this is all for forward trajectory? If the same analysis can be easily.
Yeah, I mean, see, we are interested in a particular process, right? So we just define that as the forward process. Now, in the forward process, I'm interested in how much work done and so on. Because I can, the reverse process is also a valid process. I could discuss that also, but then it's the same thing, right? I get the same results.
In that process, is the V of lambda change in the opposite direction?
V of the lambda.
Yeah.
So right now, it's lambda is just changing the, but it's therefore a different process, right? I mean,
the forward process is different.
it's different from the reverse process.
If V was constant.
Yeah, exactly. No, not constant, but even if there's no explicit lambda dependence, supposing, right? That's what I now discuss. Then the forward and reverse are the same thing.
P plus and P minus are the same.
Then it's the same thing, exactly. And then also you notice that there's no delta F. Okay, so
No, but in the forward process and the reverse process, the heat produced are different, right? So there is a time arrow anyway there.
right, yeah, no, but he's saying like it could be that the forward and reverse are the same process, because if lambda of t and lambda reverse of t are the same, are equivalent. For example, if there's no explicit lambda dependence, then forward and reverse are the same thing, right?
What if lambda is symmetric?
Both are, or if it's a cyclic process, for
Or
example.
symmetric.
Yeah, or symmetric, right, yeah. Then is also, it's, yeah. Then both are valid forward, I mean, process. Okay. So in that case, okay, so let's look at the example where, so there's no lambda dependence, let's say, but we still have a drive through the non-conservative force, which and let's say it depends only on x. Okay. And now let's choose rho naught is just e to the power minus eta v by z. So we don't have, it doesn't depend on the parameter, right? And so we, I mean, so both rho naught and rho n. So these distributions are the ideal, we take them the same. So in that case, it's clear that delta F goes to 0, and if there's no lambda, then forward and reverse are the same trajectories. So therefore, I can, so this gives me E of omega. Or if I, so now omega is just equal to beta times work. So probability of positive work is equal divided by probability of negative work is equal to the power. Okay, so in this case, there's nothing coming from del V del T. The work done is just f of x dot a. So in that case, what is the, if you are just asking what is the probability that I generate, in general, if I just look at forward trajectories, right now I can forget reverse trajectories, I'm just looking at forward trajectories. Both are for forward trajectories. I just ask what is the distribution of P, okay, of the work done. So I'll get some distribution which might look like this. So people have measured this in experiments. And so this is P of W versus W. And what this says is that the probabilities of this negative guys are exponentially small compared to probability of positive, because beta W is basically now the entropy produced, right? The work done is exactly the entropy produced, and it just says that if this is large, then this negative entropy production is very improbable. Okay, so that's the sort of physical content of this.
And Pn, for example, will depend on xn, right? So xn
Yeah,
can
but
be
it depends on xn, but it doesn't depend on lambda n, right?
Correct.
So now, but it's just like I'm starting from e to the power minus beta e of xn by z. Z is the same in both cases. I'm starting it from some like this distribution, right?
Yes.
But this distribution is the same as this because I'm integrating over all possible xn's. So it's the same thing then. Right? I mean, because my.
Okay, so the.
See, when I.
Because you are sampling over all possible x at 0 and n.
Yeah, exactly. So because my path was x0 to xn. In one case, I'm sampling over all possible x0, in the other case, all possible xn, but in both cases over the same distribution.
So you don't have to distinguish between plus and minus.
Right, yeah, exactly. So in this case, I can forget the distinction and it becomes just for, I can say, forward. Okay, so this theorem was, I think, first derived in Kuchan. Maybe 98 or 99.
So there is no lambda t.
Yeah.
Okay, so you have a conservative force in this small f, right?
Right, yeah, small f. So that's why work is completely
but the endpoints are still equilibrium.
Endpoints are, I'm choosing T0 and P0 to be the equilibrium with this potential.
Okay.
Well, there's no lambda. No.
Delta F first disappears. Sorry, delta F, free energy disappears.
Free energy because it's the same partition function at the both ends.
Okay.
So free energy is gone.
Okay.
Or I could also do this for processes which are like, if it's cyclic, it comes back to the same point. Even then, this would be the same and this would be.
So in cyclic process, what could be
Huh?
the cyclic process? 3% D minus would be the same.
Yeah, actually, I'm thinking. No, I think you can't. P plus and P minus won't be the same because it looks like you are supposed to do that. But the reverse process, it will be. Yeah, it won't be the same. But the free energy delta F will be 0, right? But it won't be. So you still have to write P forward. Right. Yeah. I don't know if you can have a cyclic process where it's the same. Maybe you can have, right? Yeah.
No, I think symmetrically.
If you do that, it's the same.
Yeah.
Yeah. You can do that.
But V can't be 0, right?
V, if it is 0, okay, I can't say why not. I mean, it looks like you can make V0. But V0, yeah, you can make V0. It's just like you drive a particle on a ring with just a driving force.
V is anyway like some reference point, right? Like
Yeah, but it's constant.
Always have some V.
But there's no, like you could either put a periodic potential or you could put a flat potential.
But if V is 0, what about the initial condition that gives you that beta?
No, then it's just uniform, right? You choose
Yeah,
it from
but
uniform
Isn't
distribution.
that beta appears here as a beta here?
Oh, this one, no, but beta is there still.
Also
in
beta
the,
delta Q, you're seeing
right,
that
yeah,
beta.
yeah. Yeah.
What are the non-conservative forces? It is there and here it is.
Yeah.
So how endpoint will get at equilibrium?
Endpoint, see, I said that at the end, if you really look at the system, it's never it doesn't reach a steady state or equilibrium state. But my choice of these functions doesn't depend on that. On whether the actual experiment is going to that state.
So find delta F, you need to know the partition function. So in a simulation, how do you find delta F?
No, you're saying here.
So
Let's say in Radzinski's equality.
Yes, the free energy.
Yeah. So how do you find in a simulation?
Simulation or experiment?
I mean, see, when this Radzinski's equality was proposed, at that time one idea was, can you actually estimate the change in free energy by doing this kind of nonequilibrium process? Okay, so you just do the experiment many times, find the work done, take an average, and that will give the change in free energy. In a simulation, okay, to find change in free energy, I don't know, there must be ways to do it. Because you can, because okay, for example, pressure is given by minus df by del V, right? So you can integrate, you can change the pressure, see how the volume changes, integrate it and get the free energy. I don't know what's the most efficient way to find in a simulation the free energy. I don't know if anyone wants to comment on that or find it. Yeah.
Work done against a linear force.
Huh?
Work done against a linear force. For example, sinusoidal potential with a drive.
Okay.
So at the end of how much it has displaced. Basically the work done against the drive force.
Right, yeah. But then you're using this type. Okay. So you see, one way you can, if you do it very quasi-statically, then you can show that delta F is equal to W. Okay. So if you do it quasi-statically, that's one way to find the, you just find it, because see, this is the idea, right? What did I write? I mean, this pressure is equal to minus del F by del V. So PdV is the work done, right? So that gives you the change in free energy. So in an equilibrium case, you just do it quasi-statically and just find.
But if the sinusoidal potential, there will be local universe. Local equilibration we can attain.
Right, okay.
From W, you can.
Right, yeah.
Positive because it will be just a Dirac delta function.
Right, yeah. Hopefully, but no, I think because not necessarily. I think, like, yeah, I remember there's some example where it doesn't, even if you do quasi-static, it doesn't go to a Dirac delta. But yeah.
Because your entropy, okay, average entropy production is that is. But it need not to be, there could be still fluctuations in between.
Yeah, so so you're asking when does this become equal, right?
Yeah,
so in general, I mean, work done minus delta F is greater than equal because this is entropy produced.
Yeah.
But when does it become equal to
yes,
zero?
so second law tells us that if we do quasi-statically, then entropy production has to be zero, double
right, yeah.
is delta F. But at the level of distribution, what that distribution if we do a quasi-static process?
Yeah, I think I remember some example where it doesn't still go to a delta function, even if you do it quasi-statically.
Sorry.
Yeah.
I think it's still very important to understand that thing. So small f is a non-conservative force which does not have any explicit time dependence.
Right, yeah.
It just depends on time through the variable x.
Yeah.
Right,
yeah.
So showing that system can have a non-equilibrium steady state, I mean, how to fix this distributions?
No, see, I still have this potential, let's say. Right? So I am just defining it like this. I am taking P0 to be, in the absence of F, whatever distribution it was.
Okay, so
this is in the absence of F. So I choose the initial condition from equilibrium distribution in the absence of F.
okay.
Then I do my, I switch
but
on
then,
this.
Then you are switching
on the force.
But then there is a time dependence, right, when you switch on this?
I think that doesn't matter, yeah. I mean, like that switching on doesn't matter.
Can f be constant, like not function of x?
Okay, so.
Yeah, it can be constant. If it's on a ring, if not on a bounded area.
That can be computed by running the simulation using Wx transition.
What can be computed?
So if you ask just taking the calculation of that, you can run the
The
simulation.
free energy?
Yeah, free
Ah, yeah.
You can run the simulation using what you know about transition rates.
Yeah, but that would need knowledge of the transition rates and which is harder to.
So if I look from equilibrium point of view, suppose my system is in equilibrium at which is with P0, right, and finally in equilibrium with in that state.
In the, I mean, when you are doing this experiment of work done, you can start with equilibrium, but at the end it's not in equilibrium.
So I mean, when you switched off that,
If I stop here and then wait for a long time, it will reach go to equilibrium. If I switch off the
in this situation, you are considering the system is finally in equilibrium.
No, I'm not. See, in the experiment, if you, let's say you started, prepared it in equilibrium, switch on the force and drive it for some time t. You measure the work done. Okay, you don't care whether it's in equilibrium or not. Yeah. Huh? But yeah, so at the end I'm saying you don't care whether it's in equilibrium or not.
No, but what is the meaning here, P and E?
No, I'm saying this is something I just choose in this is pure mathematics, you can think. I don't need that it's an equilibrium at this time.
Then you can't define free energy and all those concepts.
No, it's still, I mean, if I waited, then it says, if I switch on the force now and wait for long enough, then of course it goes to equilibrium. And the equilibrium in this for the parameter lambda t is well defined, right? So if I just imagine that the system is, like if I take polymer and stretch it to some distance, right? So the equilibrium free energy in that, for that value of the parameter is a well defined concept. Okay. And initial also is well defined. But it doesn't mean when I pull at the end it's in equilibrium. It will of course take some time.
No, one more question.
Yeah.
For example, if my system is in equilibrium, I don't disturb it. I don't disturb by external force, right? And finally is also in equilibrium. So then transition rate will govern by equilibrium status.
Right, yeah.
Right? So in that case, I will be having a difference of energy, whatever energy, I mean like e to the power minus difference of the energy in this state and in that directly proportional.
Right.
So when I am doing this work, I am taking this to that. So work is done taking from this to, I mean this work will be different from the work required from, I mean VT minus, Vn minus Vx naught. That will be different. Right?
That is a change in energy, right? That's not work done. That is just a change in energy.
Right.
Right, yeah. Or work done will depend on the detailed part.
No, that's fine. But I am saying that if I take in equilibrium, all the time in equilibrium, then I will require the work done which will be equal to the work done of the difference of these Vt minus V naught, right?
Right, yeah.
But here I will have some extra work which will be not equal to the equilibrium.
Right, yeah.
That this difference will come.
Right, yeah. Okay, let's see time. How much time? 11. Huh? Okay.
Yeah, half an hour.
Huh?
Half an hour.
I have half an hour more. Oh, really? Okay. 9:30 or it's over. Okay. I'll take 5 minutes.
Okay. Sure.
No, so I just want to, so this is actually, I have at least covered all the fluctuation theorems. Okay, of course there are more fluctuation theorems. Okay, I just want to mention that these are all valid for this time 0 to t. T is, it can be small, large, doesn't matter. There are other fluctuation theorems which are true only when t is very large. Okay. So those are called steady state fluctuation theorems. Okay, but we maybe let's not go into that. The last thing I wanted to mention is that for so there were some questions about jump processes yesterday. So Luca already talked about it, but I thought I'd just mention how this connects to whatever I talked about. So in a jump process, we look at let's say a trajectory x as a function of time. So I mean x can be both continuous and discrete. Okay, so let's I talked about spin systems which are discrete processes and so which suddenly change, but this could be continuous also. Okay, so let's if it's discrete, then what it does is let's say it starts from time 0, and then at time t1, t2, t3 there are jumps. Okay, so it's initially in some state x0, and then it jumps to, let's say, x2, and then maybe it jumps to state x3 at so now in this kind of processes, what you can look at is also, so supposing you are also tracking the energy of the system. So each of these states has energy. So E of state also depends on the parameter value that is fixed. Right? So if you are looking at the energy of this the system as a function of time, when it's in x naught, it might maybe so let's say these are the times at which the jumps takes place. So, so what does the energy do? So energy, if it's in state x naught, maybe it varies in some way. So it goes like that. Then suddenly there's a jump, so energy goes down, and then when it's in this state, here the parameter lambda is changing, so it goes like maybe it's a different function. Then at this time there's again another jump, and then it changes like this and so on. Okay, so here when you start, the energy is E of x naught at time 0. Time, huh?
X0 lambda 0.
But here it's lambda, right? Yeah. Now the parameter is changed to lambda 1. So just before the jump, it is E of, it's still at x0, and the parameter is changed to lambda 1, right? And then it jumps to the state x, so this will be x1. So it has jumped to E of x1 at lambda is still lambda 1 at this time. Then it goes here, it's still in state x1, but lambda has changed to lambda 2. And then it jumps, it's still, it's to a different state x2, lambda is still lambda. Okay, so now at the end of the process, there is some change in total energy. So that is delta U is equal to E of x at time n, lambda n minus E at x. So this is a total change in energy. You just need to look at the difference. Now this change in energy, you can break it up into work and heat, and it's clear what is work, right? So work is like, I mean, what is this difference, and then what is from here to here, what's the difference, and so on. And heat is when there's a, because this involves taking something from the heat path, right? So this happens with some rate, and so here what you need to do is the probability of forward to reverse jump is given by the amount of exponential of amount of heat taken from the path. Okay. So this is what involves absorption from the path, and this is the work done. So so you can show that the work done is basically this minus this plus this minus this and so on, and so this is some over. So here it's in the same state, lambda changes, and here it's x change, the state changes, lambda is the same. That's the heat jump. Okay, and then so this is it's easy to see that if you add these two, they just telescopically cancel, and you're just left with the endpoints. Okay, so that's the first law, and then the second law, it involves writing probability of forward trajectories, and there the main step is that so it's exactly the same formalism that I described. So if you ask what is x0 to x10. Then the only tricky part is that you have to do it for this process. So you have to ask, what is the probability of this trajectory? So I mean, then you have to ask, what is the probability there is no flip till this time? What is the probability there is a flip between time t1 and t1 plus dt1? So the probability of no flip is equals to this. So I just write it as r t1 minus t0. So this is some quantity that depends on all the rates and so on. And then there is a probability of transition, which is given by the transition probability x1 x0 into dt1. So this is probability of transition from x0 to x1, and because this is a rate, so you have to multiply by dt1. Okay, and then you will do the entire thing, so it's yes, this is basically okay, and sorry, you have to insert some so what is the probability no transition still here, transition here, no transition here. So no transition here is again r of t2 minus t1, and then again so every time you will have to insert this probability of no transitions. Okay, so now so these are of course just the transition rates given, and what is this r? So this r is what is the probability there is no transition in a given interval of time. So the probability of a transition is probability there is a transition from x to some state x prime is given by this. Probability of transition to any state is this sum over all x prime, right? This is a probability of transition from x to any other state. Okay, so then what is the probability of no transition? That is, if you just think of usual Poisson processes, then it's given by minus. So, okay, so this is integral of this object. Okay, so let's call this some r of x. So this is the probability of no transition. So this you have to just insert in all these places, and then you take the reverse trajectory, and then you see that all these r's will just cancel off because they come in the same reverse and forward trajectories. They have the same this set of r's. So those cancels, and then you are just left with the ratio of these w's, and then you use detailed balance, and that gives you that this p plus by p minus is equal to again e to the power minus beta delta q, right? Where q was just this object. So that just follows immediately from detailed balance. Okay, so once you get this, then the rest of the formalism is exactly the same. Okay, so you can just use whatever I wrote. Okay, so I think so I don't have time to do engines today, so tomorrow we'll do engines and also entropy discussion. Yeah.
So, sorry, I could not see very clearly. So, when you were writing the delta W, you wrote it as the difference of E xi lambda I minus E xi minus 1 lambda I minus 1. And then you converted it to a time integral.
Here, this one?
Before this, when you wrote down the delta U and the delta W and the delta Q, so the delta W
okay, so delta W was, let's say in this first step, it is work done is E of x0 lambda 1 minus E of x naught, sorry, lambda 0, right? And then I do E of, so in the second step it's E of x1 lambda 2 minus E of x1 lambda 1, and so on. So in general it's E of xi lambda I plus 1. Okay, so this is the general term.
But so these lambdas are changing continuously in time, or when you
Lambdas are changing continuously in time. So yeah.
So the index in the lambda is not the same as the index in the x. So when you say xi lambda.
No, so So see, x is it could be a discrete, right? It can be a single spin. So for example, my this energy that I'm writing, if it's a single spin, it could be, for example, h naught plus a sin omega t times sigma. Okay, so this is lambda of t, and this is my x. So this is of course just a continuous function of time, right? Now if it's in plus state, it's some function. If it's in minus state, it's a different function.
So the lambda i's are some functional, different functional forms of c. The lambda is.
Lambda is just this object. But the energy will of course depend on the state.
But the lambda is does not control the jumps. They control
the jumps is right. Of course the transition rate of course depends on this also, right? Because it does control. So W of x let's say I minus 1 is for example this ratio. So the transition rates of course depend on the lambda. That's the detailed balance function. And this you can see is delta Q.
Yeah, I think the same lambda.
Same lambda should be I.
Because we are fixing that.
Yeah, the transition lambda is fixed. I mean, so it's happening at lambda I.
That
same lambda.
That
gives me
So,
yeah.